This is lesson 3. Lesson 1 was an introduction to organic chemistry, and I utilized a handout that you have on Canvas to talk about organic chemistry as a whole. Then lesson 2 was the first part of this chapter, and this is lesson 3, which will be the second part of the chapter. We're going to finish talking about alkanes, particularly the alkanes that form rings, and then we'll move on to alkenes and alkynes and aromatic hydrocarbons. The formula for cycloalkanes is that when you have a cyclical hydrocarbon made out of just carbons and hydrogens, but in a ring structure, the number of hydrogens will be twice the number of carbons. And you can count them up over here in the picture if you wanted to verify that. Here you have a picture of cyclopropane. Prop, of course, means 3, and ane, single bonds, so 3 carbons forming a triangle. Bute is 4 carbons forming kind of a square, and then it's in a circle. That's the cyclo part. Cyclopropane at one time was a general anesthetic and used in surgery, and it was never a good thing, of course, if you had a successful surgery, but then your anesthetic exploded and killed the patient that way. You hate it when that happens. So we don't use cyclopropane for that application at all, unless perhaps under rare circumstances. In any case, when we talk about cycloalkanes, especially when they're smaller, they become very, very strained. It's a difficult thing to get these 3 carbons or even 4 carbons to be so close together in a ring structure. Obviously, as you go to 5 carbons in a ring and then 6 carbons in a ring, it becomes a little bit more stable. But the smaller the number of carbons in the ring, the more strained it is, the more unfavorable is its geometry, and the bonds become weaker. And so as a result, this would be much more reactive. Now this picture right here shows you a ring structure. And here, if you're going to count up the carbons would be every place where you have a angle. And so you have a 6-carbon ring structure. This would be cyclohexane. And so cyclohexane can be a chair or it can be a boat in terms of the names we ascribe its 2 geometries. The chair form is a little bit more stable than the boat form. You might also notice that we talked about the equatorial hydrogens and the axial hydrogens, just like we've talked about that in the previous screencast and in the previous chapter. The idea that you can have your hydrogens, these hydrogens here, that are in the plane of the molecule, roughly speaking, even though it's bent, and then sticking straight up into the air or straight down into the air, so to speak. These hydrogens, you would say, are axial, like they're at the North Pole and the South Pole of each carbon. And so when we think of a molecule that is flexible, with a little bit of energy coming and going, it can be either the chair form or the boat form. Now, continuing on, talking about alkenes and alkynes. Before we do that, I should mention that if you do have a let's say cyclohexane, not to be confused with benzene. So you're going to have 2 hydrogens off of each carbon. So it would be C6H12. This is cyclopentane. But then if I remove a hydrogen and instead stick on a carbon with 3 hydrogens, otherwise known as a methyl, now you have methyl cyclopentane. And you can have dimethyl cyclopentane. If I stick another carbon here instead of a hydrogen, now I have dimethyl cyclopentane, and I have to give an address for the 2 methyl attachments. So one of these carbons would be carbon number 1. The other one would be carbon number 2. Doesn't matter which way you count. So it would be 1,2 dimethyl cyclopentane. And 1,2 is often called the ortho connection. And we'll review that again a little bit later, just like we talked, especially when we talked about benzene. So if we had the 1,3 connections, we're going to learn that that's often called meta. And if we had the 1,4 connections, 1 and 4, that is often called para. So we could have para-dichlorocyclopentane or ortho-dimethyl cyclopentane or dimethyl cyclopentane when the methyl groups are on the 1,3 attachments. All right, we're ready to move on now to the alkenes and the alkynes. And as we do that, the alkenes, of course, are always the molecules that have at least one double bond. If you have 2 double bonds within the molecule, it'll be a diene. 3 double bonded carbons, you would have a triene. But with a single double bond between 2 carbons in the molecule, we're always going to end the name of the molecule with ene. And preceding the ene suffix would be the number of carbons that are in the straight chain. Several things we should say about them, that because you have this double bond, this makes the molecule a little bit less stable. So it's going to be more reactive, and you're going to have the possibility of geometric isomerism, meaning cis and trans structures. Another thing we should point out right here is that, as with alkanes, the occurrence of isomers, we always talk about species containing 4 carbon atoms or more. It's kind of hard to have an isomer of your hydrocarbon if you only have 3 carbons. There's no other way to arrange 3 carbons but one after the other, 1, 2, 3. As soon as you have 4 carbons, then of course you can get rid of one of those, make a branch, and still have 4 carbons. So you have to have at least 4 carbons to begin to have isomers. And we'll look more at table 10.3 in just a minute. Another thing we should point out is that besides the fact that they always end in ene, we have to be careful to find the longest carbon chain that contains the double bond. So, for example, it might be possible to have a big long chain like this. And let's say we have a double bond right there. No, I think I'm going to, put it right here. And I'm making this up on the fly here. Let's erase some of these. The longest chain has got to be the one that has the double bond. And so even if this carbon went out like this, we would not do that, but instead we would do this. And of course it just erased it, but I was trying to go through the double bond. So let's take a look at these isomers. They are all isomers of, well, in order to find out, we have to count the carbons. So we have 1, 2, 3, 4 carbons. So these are all going to be isomers of a compound that's going to have the but prefix, because that's the prefix for 4 carbons. And we do have a double bond, so it's all going to be butene. And the next thing we need is to have the address of the double bond. And the double bond, we want to pick the number of the carbon that is smaller of the carbons on either side of the double bond. So the double bond takes precedence over the longest chain. So if you look at this molecule right here, you see the longer chain is over here, but the double bond is closest to the left end, not the right end. So instead of making the right end the busiest end and calling this carbon number 1, instead we're going to call this carbon number 1 at the left, and the double bond then is between carbons 1 and 2, which makes this carbon number 2, carbon number 3, carbon number 4. And so we have 1 butene because the double bond is between carbons 1 and 2 of the 4-carbon chain. Now when we come over to the next isomer, you see that we have 2 methyls, one here and one here, attached to carbon number 2. The double bond is closer to the left end, so that becomes carbon 1. This becomes carbon 2, and either the top methyl or the bottom methyl can be carbon number 3, but the methyl group in either case is going to be attached to carbon number 2. So 2-methyl is the branch. The methyl is attached to carbon number 2, propene. And we could stick a 1 in there to be real specific, but it's actually the only place that a double bond could be, to be called 2-methyl propene. Now, coming over to the third one and the fourth one, you can see that we have 4 carbons in a row, 1, 2, 3, and 1, 2, 3. This one is a little more linear than this one is over here. This one is a little more polar. This one is a little bit more non-polar because it's a little more linear and symmetrical. And this is the cis form because your 2 methyls are on the same side as the double bond. And this one here is the trans because your 2 methyls are on opposite sides of the double bond. And the double bond is between carbon number 2 and 3. Either way that you go, from left to right or right to left, your double bond is between carbon 2 and carbon 3, hence the address of 2 for the butene. Finally, I remind you of what I've already said, that the carbon chain is numbered from the end that gives the double bond the lowest number. We like our lowest possible numbers when we do the naming. Now here's that table I referred to just a few minutes ago. And in this table, you can see the changing boiling points for the 4 butane isomers. Remember, these are all butane isomers, even though that name right there ends in propene. It is a butene isomer. And of these 4, you'll notice that even though they all have exactly the same formula, they have slightly different boiling points and slightly different melting points. The melting points are actually quite different. And then the dipole moment. The dipole moment is a way of talking about the strength of the dipole, the difference between the positive and the negative side of the molecule. It can be very mild, it can be very pronounced. The more pronounced or the greater the difference between the positive and the negative side, the greater is the dipole moment. The word moment is sometimes used in physics when we talk about rotary motion and rotational inertia, and it's also often used when you incorporate calculus into your calculations. And so anyway, this is the dipole moment. And so this would mean perfectly nonpolar. And then this would be more polar. It would have a larger dipole moment than this one does. Remember we said that the trans was basically nonpolar. because it was more symmetrical. But when you put the two methyl groups on the same side for your cis, that made it quite polar. But the 2-methylpropene was even more polar. I do not know why they don't have a number here for the 1-butene. Now the D here is named after Claude Debye, a chemist, and it's the unit of the strength of the dipole moment. You may see that on an AP test, just so you know what it is. And then we can talk about the amount of energy per mole that it takes to form this compound. This is, you can see the little letter F here. I think the little letter F ought to be there, but this would be the heat of formation of this compound. And you can see the heat of formations varies between a little more than 0 up to almost 18 kilojoules per mole, and the negative sign means it's exothermic. So this example 10.3, find the 6 possible alkene isomers of pentene. And so here's number 1. And we begin by putting the double bond close to one end, and whatever the end of the longest chain of carbons, whatever side has the double bond, that end becomes carbon number 1. And so this is carbon number 1, and then we number it from there on. And you can see that it's going to, because of the trigonal planar, excuse me, the trigonal planar structure around each carbon with its 3 regions of negativeness or electron density. You go carbon down to there. There's your 5 carbons in a row. Down here, the 5 carbons in a row look like this. And this is my cis. And over here, 1, 2, 3, 4. Here's my trans, meaning across from or on opposite sides of the double bond. This attachment is opposite of that attachment on around that double bond. The 1 here tells me that my double bond is between carbons 1 and 2. The 2 tells me that the double bond is between carbons 2 and 3. And so we could say these are 2 more isomers. Here is another example where my longest chain is only 4 carbons in a row. So even though this is an isomer of pentene, the base name is butene for the 4 carbons. The double bond is between carbon 1 and 2, hence the 1. And my methyl group is attached to carbon number 2. My methyl group is attached to carbon number 2, so we give the address. You will never have an attachment that will be like 1 methyl or 2 or 1 ethyl, because that would just make that carbon or carbons part of the long chain. Now we have more isomers down here. We can also put the methyl group off of carbon number 3. There it is off of carbon number 3. So even though this attachment is closest to this end of my carbon chain, the double bond is closer to this end of the straight chain of 4 carbons. Therefore, the left side with the double bond takes precedence over the attachment, which is on the right side. And so therefore, the 1-butene means this is carbon 1, carbon number 2, and my methyl is attached to carbon number 3, and here's carbon number 4. Now it's isomer number 6. We put our double bond in the middle, and we have a methyl there, and we have a methyl there, and there is a methyl there, and we have to say, what is my longest chain in a row? Well, you could go like this: 1, 2, 3, 2, 3, 4. Or if you wanted to, you could go 1, 2, 3, 4. Or you could have gone from 1 to 2 to 3 to 4. There's just all kinds of ways you could do this, but the name is always going to be the same. They're not going to be different isomers. Any way you do it, the longest chain in a row is going to be 4. But means 4. Your double bond is going to be off of carbon number 2 because that's the end that you're going to start numbering from, wherever the double bond is closest. And the methyl group will always be attached to the bond to the carbon that begins the double bond. Carbon number 2, 2-methyl, 2-butene. Now you can have more than one double bond. You can have a diene, you can have 2 double bonds, in which case, for example, you might have to have a 1,2 diene. So, for example, if I have a molecule that looks like this, I have 4 carbons in a row, so this is going to be but, and we throw the I in there. It just rolls off the tongue better, butadiene. Di means I have 2 double bonds. What is the address of the double bonds? Well, we go to the carbon that begins where the double bond is closest to, right here. This is carbon number 1, carbon number 2, carbon number 3. And so carbon number 1, this one right here, begins a double bond, and carbon number 2 begins a double bond. So this would be 1,2-butadiene. You can even have triene. Now, it's important to remember that the very, very common compound acetylene, which ends in ene, is not a member of the alkene family. It's a member of the alkyne family. Unfortunately, acetylene as a common name was around a lot longer before IUPAC got around to doing the official naming. This would be a common name you would be expected to know, and you'd be expected to know that it's IUPAC, it's International Union of Pure and Applied Chemistry. Its official name is ethine. Eth, of course, means 2. The old-fashioned name for having 2 carbons was acetyl. You might remember the name acetic acid. Acetic acid is a 2-carbon acid. Looks like this. Well, this is the old-fashioned name, acetic acid. We're going to learn later that the modern name is called ethanoic acid because eth is the modern prefix for 2 carbons. Acet was the old-fashioned name for 2 carbons, but everybody uses the old-fashioned name acetic acid, not ethanoic acid, except for the textbook that we use in honors chemistry for some reason. And we'll look more at a table of alkynes when we get to the next page. Now, by the way, notice the formula. The number of hydrogens can be determined by multiplying the number of carbons by 2 and then subtracting 2. Because remember, every time you add a double bond or a triple bond, another way of saying that is every time you add a pi bond or a second pi bond, then those 2 carbons can have to get rid of 2 hydrogens in order to still make 4 bonds. Now, anytime you have double bonds and triple bonds, and which requires you to get rid of hydrogens, you now have an unsaturated compound. When you have an alkane, the molecule is saturated. It has as many hydrogens as it can have, if it's a hydrocarbon. But when you have alkenes and alkynes, the presence of the double bond and the triple bond requires the removal of some of the hydrogens. You don't have any more, and so now it is unsaturated. Now, it's important to think about what we mean by saturated and unsaturated, because oftentimes when we talk about healthy foods, we often distinguish between saturated and unsaturated fats and oils. And the saturated fats and oils are not good for you, and unsaturated fats and oils are better for you. of course, another factor in all situations is moderation. Too much of anything can be bad for you. And yes, unless, of course, we're talking about pizza. And that was supposed to be a joke for those of you that believe everything that I say. And we'll bring this up again in just a little bit. Now, this screencast is being done just as the colorful leaves in the fall are about through, and the leaves are falling off the tree. But a very familiar alkene with that ene ending is called carotene. And you can see that it's a very, very long carbon chain. We're not going to bother to count up all of those carbons. You can notice that periodically it has some double bonds here and there, as well as in some other places as well. You'll notice it's got a 6-ring structure over there. You'll notice it's got methyl groups scattered along the way. You'll notice it's got another 6-ring structure over here. And then another thing you should notice is that it looks kind of symmetrical. The left side kind of looks like the right side. And in any case, this has 11 carbon-carbon double bonds. And the interesting thing here is that, remember, the first bond in a double bond is called a sigma. The second bond is called the pi bond. So these pi electrons that make up the pi bond, which come from the barbell-shaped p orbitals coming in side by side. In other words, if this is a p orbital and this is a p orbital, and they're coming together like this to create a molecular orbital, and where this region and this whole thing is a p orbital, of course, but these two regions are going to sort of merge together. Think of me when I held up a pair of balloons with my left hand and a pair of balloons with my right hand and tried to push them together side by side, either horizontally or vertically. One would be the first pi bond, the double bond. The other would be the second pi bond or the triple bond. But in any case, these pi electrons can be excited. And when they jump out to a higher energy level, in the blue-violet region, they leave behind the other colors, which are orange-yellow. And so the orange-yellow color is there all along in the green leaves or the green tomato. But as the tomatoes ripen and as the leaves get old, in response to the changing amount of daylight and the changing in the temperatures and the shorter the days and so forth, the chlorophyll, which is responsible for the green color, decomposes or breaks down first, leaving behind the yellows and the reds. The yellows and oranges are the carotenes, the reds and purples are xanthophylls, if I remember correctly. And then you have these beautiful colors that are left behind when the tomatoes ripen, or when the peppers, for that matter, ripen, or when the leaves begin to get old and prepare to fall off. You get all the gorgeous colors. God loves color. What can we say? Now, guys in particular, if I can address you, ladies, you can listen in. Do not do what your nerdy teacher tried one time. My wife and I, this is a number of years ago, I'm slowly learning my lesson after 50 years of marriage, that I thought it would be a wonderful thing for me as a loving husband on a romantic fall walk, holding hands with the beautiful leaves around us in the cool temperatures, to explain to my wife why we have colored leaves, and launching into this chemical explanation, which I thought was just a wonderful thing to do, and she was not so excited by that. So it's not a good thing, guys. All right. Moving right along, here's the chart that I mentioned a minute ago. And we have our ethyne, but notice the common name. Notice that when we talk about two carbons, we often use acetyl instead of the more correct IUPAC F name. F instead of ethene, we use acetylene or acetylene. Down here, by the way, this is an oxyacetylene torch. You'll notice you have two canisters here. These two canisters, one contains acetylene, one contains oxygen, and the mixture of the gases produces a very, very hot temperature, which allows you to melt the metal to the extent that you can weld metal pieces together. And here's this person wearing this safety goggle over here, protecting his eyes from the sparks and the bright light, and welding, it looks like rungs on a metal ladder or something. Of course, you might remember it more from watching the old television show, The A-Team, or the A-Team movie with Hannibal Smith and Mr. T and Face and the whole crew. Otherwise, look it up. It's last century stuff. All right. In organic chemistry, you're going to encounter, both here and later when we talked about polymers, what are called addition reactions. And addition reactions are when you add small molecules to a double bonded alkene or even a triple bonded alkene. And let's see, I should have finished talking about this up here just for the record. You ought to notice that your boiling points are very, very different based upon the structure. When you have something that is very, very nonpolar, the intermolecular forces between nonpolar molecules, especially when they're small like this, those London forces, those induced dipole forces, are very weak, and it doesn't take much energy before it goes from the solid into a liquid, if liquid at all, and then into a gas. So that's the boiling point at minus 85. Then you get a bigger molecule. You have stronger intermolecular forces. You might have a touch more polarity, and so you have a higher boiling point. And then you get an even bigger molecule yet, and it's going to have a higher boiling point because you have more electrons that can be induced temporarily to create an imbalance in the cloud of electrons around the overall molecule. And then finally, when you come up here, it gets you're even above room temperature. So 2-butene can exist at a liquid at room temperature. Room temperature is usually considered to be 25 degrees Celsius, though, of course, my classroom never makes it to 25. It's usually down around 20. Any case, back to these addition reactions. You're adding a small molecule. So this would be generic right here, example. And again, we're talking about addition reactions when you have double and triple bonds. And what's going to happen is that at the right temperature and with a catalyst, you are not going to get an X replacing a hydrogen and a Y replacing a hydrogen on the same carbon. That doesn't happen. That does not seem to be what is most stable and likely. Instead, this X will take that hydrogen's place and this Y will take that hydrogen's place, or vice versa. And you're going to get the X and the Y will be on different carbons. Now, what are the X and Y? X and Y could be the same atom, like in Brinkelhoff, or they can be different atoms, like in these hetero diatomic molecules, like hydrogen chloride or hydrogen bromide. Here we're talking probably about maybe a vapor as opposed to an acid in water. Here we have just basic water, H2O, otherwise known as hydrogen hydroxide. And if you added hydrogen hydroxide up here, we would call this hydrolysis. So hydrolysis would be a subset of an addition reaction. of the many different kinds of addition reactions. You can have hydrolysis when your small molecule that you're adding is water. You can have bromination. You can have chlorination. And those would both be halogenations because bromine and chlorine are halogens. So your addition reactions would include halogenation, and halogenation, we could be more specific when we're talking about chlorine or bromine or iodine, for example, or fluorine for that matter. So in any case, you'll notice that since my two small atoms in my species that I'm adding goes to opposite carbons, the double bond gets broken, which makes room to connect to two other atoms, and those two other atoms in this case will be bromines. And whether you put the bromines here or you put the bromines out here, I think putting them on the left side and the right side is better, because the bromines, you remember, are going to have 3 lone pairs of electrons, which make them both very, very negative, and they'll repel each other. And they'll be at opposite sides of this zigzag. So if I do the simplest form of writing this particular 1,2-dibromoethane, I'm drawing it now where this is a carbon, this is a carbon, this is a carbon, and this is a carbon. There's my 4 carbons, and then I put 1 bromine there, and I put 1 bromine there, and then the hydrogens would be understood around the other carbons. We could put our dashes there, but they would be understood. Now the F, of course, means, I'm sorry, I did way too many carbons. Let me erase that. It would just be like this, and there's my bromine. So just a straight line representing the 2 carbons. So F means there's 2 carbons. Bromo would be the attachments, and we have 2 of those bromo attachments. Where are they located? Carbons 1 and 2. You could actually put them both on 1, and that would require a different combination of temperature and catalyst and a chemical synthesis procedure. Here we are distributing our chlorines. And in this case, we have 2 chlorine molecules. And so the chlorines are going to be distributed 2 per carbon. And so that means we have 2 carbons. F, we have the chloro as my attachment. Tetra means we have 4 attachments. Notice if I have 4 carbons, I use the prefix but. But if I have 4 attachments, I use the prefix tetra. And the address is 11 and 22. Now, way back during the American Civil War, Russian chemist Vladimir Markovnikov was studying this kind of stuff, and he came up with what is called Markovnikov's rule, which we'll mention also when we get to polymers. And Markovnikov's rule basically says that in these organic syntheses involving alkenes and alkynes, the hydrogen atoms become attached to the carbon that already has the largest number of hydrogens. Another way that I've heard it expressed is the hydrogen that is in the molecule that you're adding, is going to go to where the hydrogen is. In this case, where the hydrogen is going to be one of the other carbons, somewhere in the molecule, one of the other carbons that has hydrogens. So as we look at 2-methylpropene, my hydrogen here, with the right catalyst and with the right temperature, where is that hydrogen going to go? Well, it can't go there because that carbon is already saturated. It's already got 3 hydrogens. It doesn't have room for any more. Same with that. So in this case, the hydrogen only has one place to go, and that's to the previous carbon. So in this case, this is not the best example to show Markovnikov's rule, because the only place the hydrogen can go is to the only carbon that already has some other hydrogens. So what you're going to get then is the chlorine is also going to become attached to that carbon. There's the chlorine right there. And so you're going to get this molecule right here, which is 2-chloro-2-methylpropane, because this is the carbon that's got the chloro and got the methyl. The propane refers to these 3 carbons right here. There's my long chain. And of course, the carbon that they're connected to is carbon number 2. You're not going to get this. Now, if the molecule that you're adding is diatomic hydrogen, we would call that hydrogenation. And that would happen with a catalyst, again, in the right temperature. Typically, in these kinds of syntheses, your catalysts are often a transition metal, like one of these, which can make them a little bit expensive. Now, why would you want to hydrogenate something? Well, when you hydrogenate an oil or a fat, fats typically come from animals, oils typically come from plants. But when you hydrogenate it, you make it less susceptible to spoilage. It's going to last longer. It's not going to spoil. And it also makes it a little bit more solid. Oils, of course, are very, very runny. And when you hydrogenate them, you can make them a little thicker and more solid, like with margarine. Now, the downside to hydrogenating is it's not as good for you. It's not as healthy. And so if you're not careful in terms of moderation, hydrogenated fats and oils can contribute to heart disease. And so that's why we prefer partially hydrogenated or non-hydrogenated fats and oils. So in general, when we say we have hydrogenated fats, these are fats that have been, you've had hydrogen bubbled through them at the right temperature, maybe with a catalyst. And another name for hydrogenated fats are trans fats. And trans fats, the name trans means that the molecule that's created is a trans isomer with on opposite sides of the double bond. Not all the double bonds are broken down, but so you still have a double bond and the extensions are on opposite sides, so it's trans fats, and trans fats in particular contribute to heart disease. So we typically look for foods that don't have trans fats. So unsaturated fats are good, and but when you hydrogenate them and get rid of all the double bonds, then you can get saturated fats, and those are not good. So your naturally occurring unsaturated fats are usually cis isomers, and your more dangerous, as far as your heart is concerned, are the trans fats. Now we can react these things with an alkene as well. Reaction of an alkene, with, say, bromine. I think we already talked about that. And I think I'm going to stop right there because we're already at about 40 some minutes, and we'll do the aromatic hydrocarbons in the next screencast.